Hi, my name is Trevor Arndt. This is my lab report for the fourth lab regarding Faraday's law. There are a couple fundamental concepts that you have to know for this lab, the main one of which is Faraday's law, which I've pictured on the right, which basically says by finding the change in flux over the change in time, you can find the induced current. And this phenomena can be modeled by a moving magnetic charge through a conductor, and that creates a curly electric field. You also have to know what the Biot-Savart law is, which states that a constant electric current creates a magnetic field. You also have to know Lenz's law, which is an extension of Faraday's law, which states that the induced electric current always moves in the opposite direction of the thing that is causing it. And then you have to know what magnetic dipoles, magnetic fields, and electric fields are, but I won't go into those because we've described them in the past. I said that the magnet was the system and the aluminum tube in the earthwork surroundings. I used the assumption that there were no external magnetic fields and no air resistance. My main results were the following. From the experiment, I determined that the magnet fell in 0.25 seconds, but the coding said that it should have taken 2.07 seconds. There's obviously a lot of error there. And I believe that's mostly due to the type of magnet. I bought my own magnet, and I believe that the magnetic dipole was across the short side instead of the long side, which would have caused significant error. But there also could have been human error when dropping the magnet or a slow frame rate on my phone, and I could have counted the seconds wrong. Here's my results from the experimental portion, but I won't really go into that. And then I'll show my results from the coding section. Okay, so I mostly plugged in experimental values that I found, such as here and here. And then here I use my code from lab 3. And here I use Faraday's law to create an equation that finds the change in flux over change in time, which is Faraday's law. And then basically this code takes you through and it determines the change in flux at each point. And then you can find the change in velocity, and that tells you the change in time, which is what we care about. Okay, and that was my coding portion. In the top portion, that was the model, and you can see the red and blue colors. Red means a clockwise current, and blue means a counterclockwise current. And those should be opposite, which they are. We can also see the graph of velocity versus time, where velocity has a fairly straight, it has zero gradient. And that means that the velocity is constant and the magnet is experiencing no acceleration. And here you can see my result, which I had in the PowerPoint. And now back to the PowerPoint. So my conclusions, you can obviously see that the times are very different, and I believe this is due to the type of magnet, as I said. And here are a couple questions. So what if the resistivity of the conductor was reduced as close as possible to 0? How would that affect the dynamics of the falling magnet change? Or, Ohm's law states that the current is equal to the voltage divided by the resistance. Therefore, if the current stays the same, but the resistance significantly decreases, the current would be much larger. And with a larger current, the magnet would spend more time in the tube. And then what if holes or slots were cut into the tube? How would this affect the ring current in your model? So this would cause the area of the tube to decrease. So when we were finding the surface integral, the surface area would also be much smaller. Therefore, our result would be smaller, and we can assume that the magnetic field will be smaller and the magnet would fall faster. And And that is my presentation. Thank you very much for listening.